In a previous lesson, we learned how Pythagorean triples can sometimes help us find the third side of a right triangle without using the Pythagorean theorem. In this lesson, we will examine two additional right triangles that also allow us to bypass this theorem. The first triangle we will examine is a 45-45-90 right triangle. Since we have two equal angles here, this is an isosceles right triangle. Now this triangle has two legs with length 1 and a hypotenuse with length root 2. As an aside, please note that the square root of 2 is approximately 1.4. This information sometimes comes in handy. Now please keep in mind that we can have larger versions and smaller versions of this triangle, but we will refer to this one as the base version. Now the most important point here is that for all 45-45-90 triangles, the ratio of the sides will always be 1 to 1 to root 2. Now you should also watch out for multiples of this base triangle. These multiples will typically have lengths with a ratio of x to root 2x, where x represents the degree to which the base triangle has been enlarged or reduced. The next triangle we will examine is the 30-60-90 right triangle. Here the lengths of the base version of this triangle are as follows. This time please note that the square root of 3 is approximately 1.7. Now if you are having trouble memorizing which side of this base triangle has which measurements, remember that the sides of any triangle always correspond to their opposite angles. So the smallest angle here is 30 degrees, so the side opposite this angle will be the shortest of the three lengths. The next largest angle is 60 degrees, and the side opposite this angle is the next longest length. Finally, the largest angle is 90 degrees, and the side opposite this angle is the longest length. Now the most important point here is that if a triangle is a 30-60-90 triangle, then the ratio of its sides must be 1 to root 3 to 2. Also be sure to watch out for multiples of this base triangle. Okay, let's practice. Here we want to find the lengths of two unknown sides. Now since one angle here is 30 degrees and the other is 90 degrees, we know that the third angle must be 60 degrees. Since we have a 30-60-90 triangle here, let's display the base version of this special triangle. Now at this point, we want to determine the degree to which the example triangle is larger or smaller than the base triangle. To do this, notice that on the base triangle, the hypotenuse has length 2. Now notice that on our example triangle, the hypotenuse has length 12. So the example triangle is 6 times as large as the base triangle. In other words, the enlargement factor here is 6. Now that we know our triangle is 6 times as large as the base triangle, we can find the values of x and y. Let's begin with x. Now x is the side opposite the 30-degree angle. On the base triangle, the side opposite the 30-degree angle has length 1. So x will equal 1 times the enlargement factor of 6, which is 6. To find the value of y, first notice that y is the side opposite the 60-degree angle. On the base triangle, the side opposite the 60-degree angle has length root 3. So y will equal root 3 times the enlargement factor of 6, which is equal to 6 root 3. Okay, now before we examine one last question, it's important to notice that we were able to find the lengths of two unknown sides once we knew that we had a special triangle. Okay, one last example. Here we want to find the length of one missing side. Now since we are given two sides here, we could find the third side using the Pythagorean theorem. However, let's use our knowledge of special triangles instead. Now since we have two equal sides here, we know that this is an isosceles right triangle, which means the two missing angles are both 45 degrees. Since this is a 45-45-90 triangle, we will display the base version of our triangle here. At this point, we want to determine the enlargement factor of the example triangle. To do this, first notice that on the base triangle, the two equal sides have length 1. Now notice that on our example triangle, the two equal sides have length 5 root 2. So the enlargement factor here is 5 root 2. Now that we know our triangle is 5 root 2 times as large as the base triangle, we can find the value of x. Now x is the length of the hypotenuse here, and on our base triangle, the hypotenuse has length root 2. So x will equal root 2 times the enlargement factor of 5 root 2. Now root 2 times 5 root 2 is equal to 5 root 4, and since root 4 is equal to 2, we can see that x must equal 10. Okay, before we end this lesson, let's first look at the relationship that squares and equilateral triangles have with our special triangles. First, notice that the diagonal of a square creates two equivalent right triangles. Now, if we take a closer look at one of these triangles, we can see that since this triangle has two equal sides, it is an isosceles right triangle, which means the two remaining angles are both 45 degrees. So, as you can see, there can be 45, 45, 90 triangles hiding within squares. Okay, now on to the equilateral triangle. Notice that if we add the altitude of this triangle, two equivalent right triangles are created. If we take a closer look at one of these triangles, we can see that the remaining angle here must be 30 degrees. This means that there can be 30, 60, 90 triangles hiding within equilateral triangles. So whenever you encounter squares or equilateral triangles, be sure to watch out for our special triangles. Okay, to summarize, in this lesson we learned about the properties of two special triangles, the 30, 60, 90 triangle and the 45, 45, 90 triangle.